A linear array is linearly spaced antennas in 1D dimension. Consider a linear array with inter-element spacing d, where a plane wave hits the array, and the plane wave has angle theta relative to broadside. In this case, the plane wave travels slightly different path lengths to different antenna elements. The path length difference between two successive elements is shown by L, which is equal to d sine of theta, in which d is the inter-element spacing and theta is angle of arrival relative to broadside. This path length difference causes phase shift, which is phi equal to 2 pi L over lambda, in which lambda is the wavelength. We can also model this as a delay, where phi can be written as 2 pi times fc times d times sine of theta over c, or 2 pi fc times tau, in which tau is the delay difference between elements measured as L over c, and c is the speed of light. Now let's look at the passband signal model. At the first antenna element of the array, the time domain passband signal is shown by up of t, which has a cosine term minus a sine term. It can also be written as real part of ut times e to the j 2 pi fct, where fc is the carrier frequency, and ut here is the baseband complex envelope of the received signal. At the second element of the array, the passband signal has a time delay tau, which can be equivalently shown as real part of ut shifted by tau times e to the j phi, which is a phase shift on the baseband complex envelope, times e to the j 2 pi fct, in which phi is actually 2 pi fc tau, where tau was the time delay. Therefore, the complex envelope at element 2, shown by vt, is actually u of t plus tau, times e to the j phi, where u was complex envelope at element 1. Here, it is assumed that the bandwidth of the complex envelope u is much smaller than the carrier frequency fc, and this is also known as narrowband assumption. Now, consider the frequency domain representation of u of t plus tau. The time shift tau in the time domain causes a phase shift in the frequency domain equal to 2 pi f tau. For the values of f within the range of bandwidth, 2 pi f tau will be less than 2 pi times bandwidth times tau. And since bandwidth is much less than carrier frequency fc, then 2 pi f tau will be much less than 2 pi fc tau, where 2 pi fc tau is the phase shift phi in the array. For small values of phi, since we have phi less than 2 pi, then e to the j 2 pi f tau, which has a cosine term plus j sine term, can be approximated by 1. Therefore, the complex envelope at element 2, which was u of t plus tau times e to the j phi, can be approximated by u of t times e to the j phi, by neglecting the time delay tau and considering only the phase shift term, which is e to the j phi. Similarly, at element 3, the complex envelope can be approximated as u of t times e to the j 2 phi. Now, using the approximations, we can define the array response. Consider the same linear array where the baseband complex envelope of the received signal at all elements is u of t, and the phase shifts of the received signal at the array elements are 1 e to the j phi to e to the j n minus 1 phi, where n here is the number of array elements. The received signal from all array elements can be written in the vector form as u of t times a of theta, where a of theta is a vector of size n containing all phase shifts. This vector is called array response, and it is a function of theta because phi is a function of theta, and it is defined as 2 pi d sine of theta over lambda. This is also called spatial frequency corresponding to angle of arrival theta. Now, based on the array response, another term is defined, which is called array manifold, and that is the collection of array responses a of theta for all values of theta from minus pi to pi. Another important concept that we need to introduce here is called reciprocity, which says the propagation channel from transmitter to receiver is the same as that from receiver to transmitter. For example, in this figure, if we define the antenna-to-antenna channel from the base station to the mobile user as H1, and from the user to the base station as H2, reciprocity says that H1 is equal to H2. Now, using this reciprocity principle, we define the reciprocity of array response, which says the array response for angle of arrival theta is the same as the array response for angle of departure theta. That simply means for the wave received from the angle theta and the wave transmitted with angle theta using the same array, the array response is the same. We use this principle to compare receive beamforming to transmit beamforming.